All right, so we have our talk, which is how much energy do pruned LLMs actually save by Pranav. So Pranav, floor is all yours, or should I say
Okay.
the mic?
Yeah. So this is my talk, and wait, can I change it?
Oh yes.
Is that it? No.
Okay.
Yeah. Okay.
Just use.
Yes. Okay. Yeah. So energy usage in LLMs, like look at our current world. They are popping up data centers like there's no tomorrow. And the thing about LLMs is we need to like train them once, and we are inferencing it multiple times. Like look at ChatGPT or Claude, for example. Like the model is trained like once, and a lot of users are inferencing it multiple times. And the problem right now is while inferencing an LLM, it actually uses more energy than training, because training is done once and inferencing happens multiple times. And many organizations are using LLMs. And the second thing is most of the organizations are actually using LLMs for programming. Like programming is like the one of the ways organizations use LLMs for, like, and Python is one of the most popular languages. So what is pruning? That's what I'm talking about, right? So the thing about pruning is we just remove less important neural networks. And there are different methods of pruning. The pruning which I have done in this paper is structured pruning. So depending on what model architecture you are using, you need to use different pruning methods. Like, for example, there is like a mixture of experts type of LLMs. For them, you need to use different type of pruning. Right now, for my experiment, I only did pruning on Llama family models. So when it comes to any large language model, it has multiple layers. So this over here, like it has an attention block and a GLU block, gated linear unit. So here the pruning is done in the gated linear unit, and the gated linear unit has perceptrons. So here we'll be talking about the Llama architecture. So the MLP layers, multi-layer perceptron layers of each transformer block has like in the glue unit. So it has like a gate projection, up projection, and down projection. And our pruning targets these three paths. So first, the importance scores are calculated. And for the importance scores, you can see the formulas, which are over here below. And after calculating the importance scores, the neurons with the lowest amount of importance, they are removed. And the importance scores themselves are calculated using the maximum absolute value of the neurons. So this is the experiment. This is what my paper is written about. So first, I'll take a bunch of models in the Llama family architecture. And then I prune them at different percentages, like in increments. Let's say I first prune the model 5%, then I prune the model 10%, then 15%, and so on like that. And after pruning the models, I took a Python data set and trained them using low rank adaptation, fine-tuned them basically. After fine-tuning them, I measured the amount of inference energy these models are using. After doing everything, I calculated the amount of accuracy these models are losing using the human eval score. The thing here is you may be thinking like when it comes to large language models, let's say large language models aren't usually specialized in one task. You can ask them about to write an essay and a large language model will do that. So instead of generalizing it, what I'm doing here is I'm only testing these large language models on Python programming challenges to understand like how their accuracy is affected. So this is my experimental setup. for this experiment, because I'm measuring the amount of energy these LLMs are consuming, all these experiments are done in Chameleon Cloud bare metal servers. So you may be wondering what Chameleon Cloud is. It's like all colleges came together and they are basically sharing their infrastructure. It's funded by the National Science Foundation. So yeah. So the models I use are Llama 3.2 1B model and the 3B model and Llama 3.1 8B models. So you can see the specs I'm using, like 4x A100 GPUs. I use them to fine tune the models. And for inference, I used like RTX. So for fine tuning, I use those. And for inference, I used RTX 6000. So for inference, I use RTX 6000 with 24 GB of VRAM. The reason why I use those instead of A100s was because A100s are pretty hard to get by, like even in Chameleon Cloud. They cost a lot of credits and you need to reserve them. So I couldn't get the reservation to do my experiments. So I used like RTX 6000 model for that. And the fine tuning, I did it with those specs, like rank of 128 and alpha of 32 and dropout of 0.01. And they are, of course, fine-tuned using a Python code dataset. So my experiments, like the accuracy won't be different. Like the thing about base models is that you need to like fine-tune a base model for only Python-related tasks for it to actually excel in the accuracy. Yep.
Small question.
Yes. Yeah.
Say 100 prompts times 10.
Oh, yeah. Wait a second. Where is it?
The last.
Oh, yeah. The way the energy is measured. I'm sorry, I didn't see that over here.
So how did you?
Yeah. So to measure the amount of energy these models are consuming, what I did was I took like 100 prompts, 100 random Python prompts. I gave these 100 prompts to the large language model. I ran the experiment like 10 times. After, like there will always be some outliers every time you run the experiment. After removing the outliers, I just took the average out of it to measure the amount of energy the large language model is consuming. Yeah, that's how I measured the amount of energy. The Python data sets, like there's a Python data set. Yeah, like the ones which I'm using for training.
Okay.
So I just randomly took 100 of them from that.
Standard set of prompts.
Yes,
Okay,
yeah.
For basically this kind of experiment.
Yeah, like for training it, that's how you train it. Like there are prompts and there are solutions.
Okay.
So like that, I took 100 of them from that.
Are these prompts, are they fairly complicated prompts or?
No, they are not that complicated. Yeah, because they are using small models. It's not like I'm not using a 100B model or something. So I just took the simple prompts. So these are the parameters. Here you can see the base model, and you can see a linear drop in it. So if you prune it like 5%, the parameters kind of get reduced. And for 30%,
You're saying there's a linear relationship?
Yes, that's the point I wanted to make with this graph. Yeah, there's a linear relationship in the drop. So this is for the 8B model. So here are the human eval results. When it comes to the human eval, it's not exactly linear. It's kind of non-linear. It just falls down over here and goes like this. You can see the same for the 3B model too. Just it's not exactly non-linear.
But is it if you just make what's the name of it? A best fit, is that the term for it? When you're tracking, you go back.
Yes.
There is a general pattern.
Yeah.
Going down more or less in a linear fashion.
Not exactly.
Because it dips and it's like a wave.
Yeah.
But especially like right on the right.
Yeah.
You see it go up and down, up and down. So the LLMs are not deterministic.
Yeah. The thing about this is, as you remove the neurons, at one point you'll be removing the important neurons. Once you remove the important neurons, it just suddenly falls down.
Okay.
Yeah, that's the point I wanted to make with this graph. Because if you remove the redundant neurons, it's affected, but not that much. Once there are no redundancies, like you remove everything, it just falls down.
Okay.
So here you can see the 8B model. Even here, it just falls down over here. Like the drop from here to here, like from the base model to 0.5% and 0.5% to 10%, it's more. So I think these are mostly errors, or it's basically noise. That's what I'm thinking. But yeah, this is for the 8B model when it comes to the human eval score. And the human eval score itself works on the probability. It works on the probability. Like it's the amount of probability that one problem from the human eval database will actually pass everything, something like that. Yeah. So this is the interesting part. If you look at the inference energy, this is the base model. And you will be thinking like less number of neurons and the amount of energy consumption should also be less, but that's not happening. If you look at the 30% part, it's actually more. This is the base model, and this is pruned by 30%. So you
So
can
you're saying once you produce the energy consumption went back up to the same amount?
no, it's actually increasing
It's going
sometimes.
even higher.
Yeah.
But it's basically the same or more.
No, it's not the same. It's more.
But there's a point of no gains, in fact, loss.
Yeah.
You can trim it a little bit, but you can't trim it all.
Yeah, if you trim it a little bit, the energy consumption actually decreases. But after a certain point, it somehow
Is
rises.
that because it's having to continue to run new tokens to get the right answer?
To be honest, I don't really know, because that's actually one of the question of this experiment.
Because I would say, like, if the error rate started going up,
Yeah.
that would explain the energy consumption, because now it's trying to validate something that it doesn't really have any evidence for, because you've already pruned the redundant information that's there.
I don't think it can do that. The reason is these models are run locally and they don't know what's error and what's not an error. Yeah. So you can see the same for the 3B model. Like it kind of falls down and suddenly increases.
That's Llama 3 one.
Yeah, that's Llama 3.
So you said there's no error ranking within Llama 3 one.
Like, what do you mean by error ranking, to be honest?
So,
Exactly.
for example, if you ask a question, and,
Yes.
before it answers it, does it go and do any kind of activation layer checking between the layers, or is it just use the?
No, I don't think it does anything like that, because to be honest, I actually saw the answers for it when I asked the prompts, and some of the prompts are like gibberish, literally. If it had any error correction, I don't think it will output gibberish.
Well, it would be gibberish probably after you basically delete it.
Yeah, that's what I'm saying. I don't think it has any error correction in it.
Well, there's how many layers in Llama 3.1 or 3.2 for the activations?
I
14,
think,
right?
yeah, I'm not exactly sure. I couldn't just suddenly think it from my mind. So this is the inference energy of the 8B model. And even here you can see some pattern. It just falls down and it kind of flatlines. Like it's not linearly decreasing. That's my point. Because if you actually decrease the amount of neurons in a large language model, mathematically speaking, the amount of energy consumption should also decrease linearly. So my point with this thing is, it's not exactly, the problem isn't with math or something like that. The problem is actually with the hardware. Because the matrices are incomplete, GPUs are not adapting properly. Like they're actually consuming more energy for doing the matrix multiplication. So if you look at a few papers and internet in general, they'll be like, if we prune the model more, it somehow consumes less energy. Like it's mathematically true, but when it comes to the hardware in real world, it's not true, because GPUs are not, don't work like that. Well, that's at least the theory.
But it could have been the algorithm itself.
Yeah, even that's a possibility. This is just a theory. We didn't verify it yet, but this is the experiment.
So does it destroy the overall structure of the model?
Yeah, that's what we are. Yes.
In detail, do you know, to go into more detail on exactly what pruning means? If
Yeah.
you say you destroy it, how exactly is the model laid out in memory? And what I'm wondering is it now sparse or is it still dense?
No, it's not dense, it's sparse. I mean, that's the entire point of pruning, right? Like,
Yeah.
So
So if you're pointing this out, I immediately jump to a caching problem.
yeah, even that's a possibility. Like, yeah, that's also a possibility. Because I didn't really check why it's happening, but this is just the finding of my paper experiment. Because if you look at papers, some papers only talk about like energy per token consumption. And I personally believe that's a bit inaccurate because sometimes the token, the output, it just generates gibberish. And when it comes to energy per token, you are also including the gibberish part.
If you look at the dense matrix multiplication afterwards, see it change in the tensor cores.
Like, what do you mean? Like
When the tokens are calculated, the multiplication matrix structure that's built into Llama 3, 2, and 3.1. If you're destroying the model, then it stands to reason the overall structure of the model would be.
No, we are not changing the structure of the model, by the way. Yeah, the only thing which is changing is the matrices. They are becoming sparse instead of being dense. So these are our contributions.
How
Well,
do you know you're not destroying the model?
because I checked it.
So what method
Yep.
are you using for
Oh,
pruning?
sorry. Yeah.
But you showed that there was maybe I misunderstood. You showed that there was a degradation in the evaluation.
Yes, the accuracy
So-
decreases.
Oh, it's not doing as good of a job.
Yeah, because you are removing the neurons, so that's expected.
Have you compared this finding to like existing pruning techniques?
I didn't use any new pruning techniques. I just used this is like the most simple pruning technique. I didn't use any novel pruning technique.
I just did a quick Google on it.
Yeah.
I was just wondering about the energy consumption and why it would go up. And primarily, it's a known fact that once you prune the model,
Yeah.
create a sparse environment, then the overall structure of the model is destroyed.
Yeah.
And it has to resort to a different multiplication style
Yeah.
to get the answers.
Mhm.
Therefore, you would see an increase in energy.
Yeah.
It's using a less efficient.
Yes.
How do you know if that happens?
Well, I mean, to be honest, I didn't do that experiment, so I can't say anything. It's just a theory.
It says that the CPU and the DRAM spike.
See, if you have different instructions that are being generated, how do you know which instructions are happening? How do we actually get inside of Llama itself to see how this is from? I want to actually get down.
That's a nice question.
New visualizer that came out of Claude, and they were able to take Fable 5 and spread it out in a visualization, like all the neurons as it's firing. That I don't know if that would give you granularity.
Are you able to do instruction sets the old-fashioned way and see the instruction sets that they're executing when they're debugging on a GPU? I have no idea exactly how. Like, I've done shader programming, so whenever it comes to whatever's happening on the GPU, like everything is always high level, compiled at runtime, and then sent over the rest of the GPU. I assume that this is working the same. So I assume that you would not only get the different instructions, but you would actually be able to see the way that the language is built is coupled together before it is compiled. But if what I said applies here, I really doubt it.
It's a Google away. So you just Google it, look at it. Basically, it breaks the vectorized memory alignment. So the hardware maximizes the process speed and via coalescing memory access for vectorization. It increases the workload. That's it. And that's why you see the energy spike.
So
Because it's using, it forces dense hardware to do sparse math, which obviously is going to spike energy.
yeah, but it will also be interesting if we do the same experiment on TPUs instead of GPUs.
But why would that make a difference? The hardware.
No, like it's a different hardware, right? Like
Do you think the hardware would be able to deal with a broken model any better?
Yeah, I mean, depending on the model, like TPUs work differently, right, compared to
That's like saying
GPUs.
if I have a Ferrari and I take a wheel off,
Yeah.
it's gonna ride fine. Versus if I take a Honda and take a wheel off, if it's 3 wheels, it's 3 wheels. It's still missing missing something that's going to give it stability. Once you destroy the model, don't you destroy the ability to audit it and traceability is gone, availability is gone.
To put it simply, if the whatever hardware we are using can do matrix multiplication in a mathematical way, like as close to mathematical as possible, like in theory as possible, I don't think this will be a problem because they don't have to switch any algorithms or anything like that.
Maybe, and not casting aspersions, but it
Yeah.
seems like there's some superficially we can agree that there's problems with trying to reduce the model from the state it was. Maybe the more, if you're interested
Mhm.
in consuming less, would be to make the original model more efficient.
Yes.
So instead of having coding with a general purpose LLM,
Yes.
you had a Python LLM, and it would not know anything else, then you could code just Python.
Yeah.
Potentially, and spend less bits.
I think even if you use the
model.
Oh, no, I'm not going.
You're saying
I'm saying forward engineering, not backward
okay, got
engineering.
it. Okay.
Forward engineering seems to be, because the math is too hard for me right now at my age, but what it seems, the tendency that I see is the fact that if you train it up front,
okay.
which there might be a business case or not, but forget that for the moment. Training models for very specific tasks will give you the dense matrix that you need so that then you don't have to generate it by removing stuff.
Well,
No, definitely, yeah.
it has
So
a
then
point.
don't
If
have,
you
like, a bunch of
train a
extra
model for a
data.
specific task, it will of course outperform any of this.
Yep.
But this is just my paper. Like this is like a specific task I did over.
But what's the use cases?
Well, I mean,
Oh, no, I get the purpose of it. It was a good experiment.
this is
What
just
the purpose? That's what I'm trying to get.
like
The purpose, the way I
Break the
understood it,
model and
tell me-
it uses more energy? I don't get it.
no, if the experiment blew up. So I'm
Okay,
typing.
yeah, you delete stuff that you need, yeah, it don't work. That's common sense.
I mean-
It's like me deleting lines from my code. It's less lines, it's smaller. Now it's not working.
here-
Okay,
But
I don't
here's where I saw the value of at least exercising.
okay.
Not necessarily the vector space is applicable towards the task that you're doing. Right? Because if I remember correctly, everything is on a vector space, multidimensional. Am I mistaken about that?
Sorry.
yeah,
Okay.
okay.
Now, the problem is, if you don't understand how the vector space was aligned to begin with, if you're just pulling random
That's
things
my whole
out.
point. That's why I just don't understand this approach.
But if you could actually, theoretically, if you could understand how the model was laid out to begin with, then you can reverse engineer.
Maybe. for
But
sure.
then that might be too hard. It
To
might
me,
just
to
be
me, that's a more accurate reference to pruning versus deleting.
Yeah.
To me, this should not be called model pruning, it should be called model deleting.
Okay, yeah,
The pruning is a very specific, like,
it's got a very
Not just
specific
like
semantic.
just ripping stuff out without a process or a thought to see what happens. Like, oh, does the energy go up or down if I tear it up? I don't know.
I mean,
Why would that matter to know?
I would say if you if you make the dense matrix sparse, I think you'll get the same results anyway.
No, if you're forward engineering, and again, this is all hypothetical, right?
Okay.
But if you're forward engineering and training the model just to do specific things, for example, vision models.
Yeah, I mean,
They're not meant for.
yeah, but your point is completely different to pruning. Like it's yeah, I get it because there are also people who do exactly that. What you're saying.
But he's doing a very specific thing, and I agree with him.
Okay.
Calling pruning
Yes.
when you're actually chopping up things at random.
No, it's not exactly at random.
Okay,
It's
so what's the process of?
Yeah, that's what I want.
as I told you, we take the maximum absolute value. It's not exactly random. Like
Oh no, that's.
I mean, right. It's just like saying, let me just delete all the smallest stuff. Like, that's still not a real scientific approach.
like
But it's like,
It is scientific, but it's.
I
guess
mean-
a little bit, yeah.
well,
It's-
I
it's-
mean,
It's reductive. It's a reductive approach So you do have some control over the experiment because you know how much you deleted, but it doesn't tell you like what you're like where you're deleting it or what aspects or
And you know
what
what the
effects it's
weight
gonna have.
You know
I
the
mean,
weights
but
different.
how are you gonna know what effect it's gonna have, like before deleting it?
That's what we're asking you. I don't know.
No, seriously, like when you
No,
said,
that's what we need to know, right? That's what we need
yeah,
to
because that's much more complicated, and like this is like the first stage.
Yep.
You will eventually go to that stage. Like, how are you gonna know the end result without even doing like the first step?
Basically,
And I think
I guess I can see that. I can appreciate that.
the reflection of as a group, because we're
Mhm.
having a scientific discussion here.
Yes, yes.
Is that one approach would be to figure out if you're going from a open source model,
Mhm.
and because they're open source, I guess, they tell you the process on
Mhm.
how they get to the model.
Yes.
If you can trace the parts of the language model that are related to, I don't know, Java,
Mhm.
and pull them out,
Mhm.
Yeah.
Yeah.
and everything but, or just say, what are the pathways for Python?
Yeah.
If you go from that and then prune the vectors that come out of the
Mhm.
everything but the Python,
Yeah.
boom, you've got a Python LLM.
But yeah, actually, that makes me think something. Let's say you're speaking in English, for example, but to speak in English language, you need to also know some other things, right? Like, let's say I went to go out on a walk. Let's say you just said that. Yes.